All right. Good afternoon. So today we are gonna have our last lecture. We are finishing chapter 6. Um, Before we talked about the situation, we have only one load, which makes the normal stress, and we introduced different failure theories for the fatigue. One of them was Goodman, Gerber, Soderberg, and ASME elliptic. So now we are going to move to the case we have combined loading. But before I go through this case, which we have combination of the loading, including bending moment, torsion, and axial loading, I would like to look at the situation where we have pure torque. So before we go through the combined loading, we assume we have pure torque. When we have pure torque, we are going to use Goodman criteria. If you remember when we have pure bending moment, the Goodman criteria looks like sigma A over SE plus sigma M over S ultimate equals to 1 over N. Where we have pure bending moment, it's going to make the alternating and mid-range stress. So the Goodman criteria is going to look like this. When we have pure shear, the shear is going to make torque. We are going to have alternating torques and mid-range torque. The alternating torque is going to make alternating shear stress, and this is going to making the mid-range or mid value for the stresses. Now I replace sigma A by tau A and sigma M with tau F. For SE, if you remember, when we wanted to calculate SE, one of the factors was load factor. Load factor for torque, it's going to be 0.59. So when I'm moving from bending moment to the pure torque, I don't need to do anything. I just use the corresponding factor, 0.59. I modify this by applying 0.59 to the SE. So whatever is the SE is going to show up here. But for S ultimate, I'm going to change it to SSU, or SSU would be ultimate strength for shear, which is going to be 0.65 times S ultimate. So these are coming from experimental results. So the recommended value would be 0.65 times S ultimate. Then you are going to apply the Goodman criteria for pure torque. Good?
So most it's like that, where you can get materials, properties, right? Sometimes you're supplied a shear stress or shear stress that applies the same thing as SAC or
In a strain or shear stress?
shear stress.
This is the strength. This is,
It's shear stress, strength is what it
yes.
is. So and like for like 1045 per hour.
Oh, okay. I think that it's gonna be SSY. Yield shear strength.
Okay.
It's different than this one that we are using that. For this one, if you remember, based on the maximum shear stress theory, SSY is half of SY. You remember this.
Okay.
And for distortion energy theory was the square root of 3.577. SSY was 0.577 SY. But this is something different.
Okay.
This is ultimate strength. This is the legal strength for the shear. Any question about this before we move? Yes.
So we started with the bending moment equation and made the torque equation?
Whatever we covered so far, it was about the normal stress, which is coming from the bending moment.
Okay.
What if we have pure torque, no moment? We still can use the Goodman criteria to do the failure analysis, but instead of using sigma A, we are going to use shear stress for alternating component and mid-range component. SE is not going to change, just we should apply the new factor for the load factor. And S ultimate is going to change to the SSU, which is going to be this, 0.67 times S. So this is how we can use this for the pure torque. But now I'm going to move to the general case where we have combination of all loading. So we might have the alternating component for the axial load. PA and PM would be representing axial load for alternating component and mid-range. These two making alternating stress and mid-range stress. Bending moment. Bending moment can make sigma A for bending, sigma M for bending. And torque, alternating, mid-range, they can make tau A, tau M. If you have combination of these 6, 1, 2, 3, 4, 5, 6, 6 different stresses on fatigue analysis, how can we deal with these problems? We use the von Mises equation. If you remember, von Mises stress was sigma x squared plus sigma y squared plus 3 times tau xy square root. It's when we talked about the distortion energy theory, we defined the von Mises equation for the stress. So what I'm gonna do, I'm gonna define one sigma prime A for von Mises and one sigma prime M for von Mises. So the sigma x that I have, it's a normal, so we don't have any sigma y. So this equation is gonna change to sigma x squared plus 3 tau xy squared squared. So the normal stress that I have here has two terms, one coming from axial, one coming from the bending moment. Now for alternating components, I'm gonna add them up. I'm gonna add this plus this, then I'm gonna square them plus 3 times this square and get one value for sigma prime A. So I'm gonna use here and there and do the analysis. So this is the idea. But we are gonna have some other factors incorporating in this equation. It's starting from fatigue concentration factor for bending moment. If it's involved, we should multiply this by sigma A. For the bending, we add Kf for the axial times this. We should divide by 0.85 because it's axial. So we are going to divide it by 0.85. So Kf for bending multiplied by sigma A for bending plus Kf for axial multiplied by sigma A for axial divided by 0.85. This square plus 3 times Kf for the shear. For the shear stress for the torsional times tau A square and entire of this square root. It's gonna give me the von Mises term of alternating component. So for the mid-range, we are doing the same, except here 0.85 doesn't show up. So Km would be Kf times for the bending times sigma m for the bending plus Kf times sigma m for axial square plus 3 times Kfs tau m three tau square, and the summation should be a square. So now you find sigma prime A and sigma prime M. For example, you want to apply the Goodman. The Goodman, one of the factors is the load factor. Load factor, we have combination of the loads, axial, bending, and the torsion. Since we already consider this factor here, we are going to use Kc equals to 1 because this factor is already considered on this factor. So 3 is going to cover 0.59, so we don't need to multiply to have Kc equals to 0.59. We just use Kc equals to 1 when we have combined loading. Then you plug in here, and if you have factor of safety, you incorporate that, or if you want to find the factor of safety, you can find it there. Any questions so far?
What's the SU stand for? Is that for S ultimate or?
Yes, it's
Okay.
ultimate.
So that is SU. Okay.
Yes,
Cool.
it's a. I just made example for the good man. So
Okay.
if you want to use the other criteria, you can use. All right, let me work on one example. Any question on this? The example is gonna be a comprehensive example. It covers many topics that we covered on the fatigue. Before we go through that example, for the combined loading, if we want to test or find the factor of safety for against the yielding, and for yielding, we should divide SY by one term, and that term of stress is coming from this. So you have sigma prime A, you have sigma prime M, you can add them up squared plus 3 times these two squared. You find that term and you divide it by you divide S5 by that one, and to find factor of safety for yielding. Or there is another way that you can find sigma prime max. You just add sigma prime A by sigma prime M, and you divide S5 by sigma prime max. So either this one, which is using sigma prime A and M, or this one, which is using sigma A and sigma M and tau A and tau M. So either way, you will get very close results. One mechanical component that we didn't have time to do the have a complete analysis for that is power screw. So you put a weight on the top of this power screw, apply torque here. It's gonna moving up the weight or moving down. So depending on the application, it can move it up or moving down the weight. So this example is about the power screw. So the material of the power screw is given, the alternated strength and yield strength, and it's a ground finish. When it goes up, when it's moving up, it's gonna move the weight of 15 kilopounds. And the torque that we applied to the power screw is 3,000 pound-inch. In return stroke, when it's coming down, the force that we are gonna move down is 2 kilopounds, and the torque is gonna be on the opposite direction, and the magnitude is gonna be 300. So So if the load or the force that you put or the weight that you put on the power screw, and this is the power screw. On the top, you can see a disc. This disc is representing this part, and this side is gonna be just this side of the this part of the power screw. So the fillet for this is the radius of the fillet is 1/8 inch. This diameter is 1.75, and this diameter is 1.25 inch. So we were asked to investigate the failure on this power screw. It doesn't talk about fatigue or something else, but when I look at the force, I can see the force is changing. Force is changing from 15 to 2. Also, the torque is gonna change from 3,000 to negative 300. So it's gonna tell me it's a fatigue analysis problem because the load is varying over the time. So this force is making the axial load, and this torque is making the shear stress. So sigma max is gonna be F max divided by area. Maximum load is 15 kilopound for the force. 15,000 divided by pi over 4. We are designing for the smaller diameter because it's gonna fail like that cross section. So 1.25 over 2. It's gonna be 12.2 kpsi. Sigma mean then we have F mean divided by A, 2000 divided by pi over 4, 1.25 square. It's gonna be 1.63 kpsi. Shear stress for the maximum shear stress when it's moving up at 3016 torque times pi e power 3, 16 times 3000. 7.82 kpsi. Tau mean, the torque is gonna be negative, so I should consider the negative side. It's important because the value for alternating and the mid-range is gonna change when I add them up or subtract. So negative 300 negative 0.782 kpsi.
It's a smaller area.
Yes, smaller.
5 on
Yeah, that's a good question.
there. Yeah, because it says diameter 1.5, and if you've got a radius of 1/8 of an inch, you're
It's right
reducing.
That's I mean, I should fix this. It should be 1.25.
Oh,
1.25 is correct.
Which one's supposed to, so the 1.5?
So we're doing the
1.25.
correctly, but we
Just
need to
revise
take this
these to 1.25. The smaller diameter is 1.75. This one is 1.25. Just fix that.
but if you're going from 1.75, you're taking off 1/8 of an inch on either side with that radius. You go down to 1.5 inch. You wouldn't go down to 1.25.
So the radius would have to be shorter.
Yeah, the radius would have to be recorded.
I don't get. So the
He's saying-
smaller.
He's saying the slide is right.
Yeah, the slide's right because you've got a larger diameter at the top of 1 3/4 inches. If you've got the radius on that fillet of 1/8 inch, you're taking off a 1/4 inch total in diameter, so it would be
Ah.
minor diameter 1.5.
No, these two are not related to each other. I mean, the fillet can be anything.
Curvature, not the thickness.
Yep. It's a radius of the curvature of this side. The fillet can be sharp or
Gotcha.
so I can put it 1.3.
Okay.
Make sense?
Let's see what's
All right. So since the maximum, we have maximum value for the normal stresses and minimum value for the normal stresses, we can define alternating, which is the absolute value of sigma max minus sigma mean divided by 2. This minus this, it's gonna be 5.29, and the mid-range would be sigma, not absolute, shear stress also tau max minus tau mean divided by 2, 7.82 minus 0.782. You will get 4.3 and tau m. Just add them up, get the average. You will get 3.52 kPa. So since I have combination of the loads, I should use this equation that I showed here. These two. But since we have discontinuity here, right here, I need to find Kf for the axial. This term is gone because we don't have any bending. Kf for the axial and Kfs for the torsion. And it's going to be applied here, right there, and in these two parts. So next step is finding Kf and Kfs. Kf, if you remember, 1 plus Q, Kt minus 1, Kfs was 1 plus Qs, Kts minus 1. To save the time, I'm just showing the graph. Just need some steps of the calculation. So for Kf, we need to find Kt. Look at the table, figure A15, find the case where it's going to look like the power screw that we have here. We have axial load with circular cross section, different diameter. A15.7 is going to be the figure that we are looking for. Find R over D, R, the radius of the fillet is given, divided by a smaller diameter, you can find that. And depending on D over D, 1.75 divided by 1.25. And find Q right here for the Q. The radius is 1 over 8, which is somewhere here, 0.125. Find the material, it's given its ultimate strength, and find the Q. I can read Q equals to 0.86 coming from figure 620. And KT is gonna be 1.85, figure A15.7. I will find KF equals to 1.73. If I plug in the numbers there, I will find KF. For KFS, I need to find KTS. So KTS
No, I mean like this equation. Like over here, there's no actual Q. See?
the shear stress is coming from the torque or torsion. Find that figure which is going to give you KTS for the shear stress. We have the circular cross section with a different diameter, which is under torque. Read R over D, you already calculated there for the first part. D over D has been calculated. So read KTS. So KTS is going to be 1.4 coming from A15.8. And QS figure 621. We are looking for the notch sensitivity. How much the material is sensitive to KT. So we are the radius of the notch is 0.125. Find the corresponding curve and the QS, which is 0.93. So we can find KFS equals to 1.372.
Dr. Gaffney,
Yes.
if we were to have a problem where we would have to use these tables on the final, would you give us like, do you want us to read it directly off the table or the chart rather, because we would all probably get different answers, or would you give us like a list of potential?
No, I mean, I mentioned before, for example, if you read this 0.90, that's fine. So,
Okay.
but if you
there will
read
be some leanings.
So-
0.45, it doesn't make sense.
Okay.
No, I'm not looking for exact number because it's just a figure. You cannot be exact.
Thanks.
Yep.
Yes.
So now we can find the these are the alternating and mid-range value. Now I can find the actual value because I could find the fatigue concentration factor. So sigma A for actual is Kf times sigma A. Kf was 1.73. Sigma A is 5.29. I will get 9.50. Sigma M for actual would be Kf times sigma M, 1.73 times sigma M, 6.93, 11.99. KPSI. Tau A for actual would be KFS, S representing shear. Tau A 1.372 times 4.3, 5.89. And tau M for actual so now you have everything to find the von Mises terms. I'm calculating sigma prime A and sigma prime M. And von Mises stress. Sigma prime A would be a square root, it has a square root at the end. This times this is gonna be 9.15. 9.15 times the coefficient of 0.85 s squared plus 3 times tau A actual, which is 5.89. 14.83 KPSI. So 9.15 is coming from here. This term is 0 because we don't have any bending. Sigma prime M 11.99, no coefficient of 0.85. 3 times 4.82. So if we want to find, if we want to apply the good math, it's going to be sigma prime A divided by SE, sigma prime M divided by S ultimate equals to 1 over NF. Factor of safety for fatigue. I could find sigma prime A, it's right here. I could find sigma prime M right here. SE would be KA, KB, KC equals to 1. Combination of the loads, the load factor should be 1. KD, KE, KF times S spring E, which is half of SY. It's machine, so we can find Ka from here. I'm just writing the values. I don't go to the calculation. Ka 0.87, 0.858. Kb is a size factor. You have a diameter, a smaller diameter is 1.25. Just plug in there and find Kb. So this is Kb, 0.85. And Ka would be 0.876. Kc is 1. Temperature is 1. The other factor would be 1. S spring E is half of Sy. Which was 112. This one was 112. Oh, half of S ultimate, sorry. Not SY. SE is, S spring E is half of S ultimate, which is half of 148. So if I do that, I will find SE equals to 55.62.
It's SE and then it's- Yeah, it is the first and the next slide.
So,
Now I'm gonna plug in the numbers here. 14.83 kpsi divided by SE, which is 55.62, plus 14.62 divided by 148, which is S ultimate, equals to 1 over n. Solve for n, it's gonna be 2.77 for fatigue. Against yield, Sy divided by sigma prime n plus sigma prime n. This is how you can find factor of safety against the yielding. This is against fatigue, this is against the yielding. 112, sigma prime A 14.83 plus 14.62. 3.8031 kPa. So if you compare these two, if the failure wants to occur, it's gonna be about due to the fatigue.
wait, why did you label the yield safety factor with KPSI? Okay, cool. Just making sure. At least I understand something.
Yeah.
Yeah, well.
There should be no units on factors.
You go.
Unit is times safer.
So make sure that you fully understand about this example. I will post a lecture as well on Canvas if you want to review it again. The final exam would be 3 to 4. I just designed the first problem. So 3 to 4 problems. It would be on Science Center Hall. If I just asked to reserve the room. If they change it, I'll let you know. But it's going to be on over there. Saturday, May 11th, 1:15 to 3:15.
Anything specific we should be studying, looking real hard at?
Everything.
It's a comprehensive exam. So everything but for the fatigue, make sure that the examples that we did in class, you have fully understand. One problem from failure theory, for sure. One problem from fatigue. I have not decided about.
Will we see anything basically like? Will we see a problem similar to test 1 and some problem similar to test 2?
Yes.
Okay.
Or will we see?
So will we see something like a buckling problem?
I cannot. If I give you a buckling problem, yes.
Good try. I have another question.
I need a volunteer to pretend that.
I appreciate the level of stats that you have thrown at me.
Sure.
Straight sound.
Dr. Gaffney, would we need drawing tools?
Drawing tools.
We're gonna do more, sir.
Dear God, no.
Please no drawing tools.
No.
Cool.
No more,
No drawing.
No drawing.
Thank you.
Dude, I'm gonna bring a coffee cup.
I did pretty well.
You say that like you wouldn't already have it. Yes.
Red Bull and coffee.
No,
That's
Before you leave.
you joke with Patty, you should feel bad.
But I don't.
So like, also remember, any small
Yes, thank you. Yeah.
welcome.
Yeah, seriously, I feel
Yeah.
really stupid for that.
Okay,
I had some jokes this
Thank
way.
you.
Yeah.
It's just letter grades.
Thanks, Mike.
What do you think? This to the right here, like an underline.
Let's not pretend.
If you have any question before the exam, you can stop by my office next
Oh, we will.
Friday.
It's too big. It's in my, I don't.